So, this is lecture 26 of basic calculus 1. In the last lecture, we had introduced the notion of definite integral. So, given a function on a closed interval a b to r, to compute its integral or definite integral, what we do is divide that into many subintervals. So, those points, grid points which are the endpoints of the subintervals, set of those points is called a partition. Then we have defined the norm of the partition, which is maximum of these subinterval lengths, and then we go for a choice set of points. Inside each of the subintervals we choose a point C I. Then we form the Riemann sum, which is summation of f of C I times x I minus 1. So, this sum, if its limit exists as norm of p goes to 0, that is the subintervals length becomes smaller and smaller going to approaching 0. If that limit exists, that limit is called the definite integral. So, today we will look at some properties of this definite integral, which will help us in evaluating integrals of complicated functions if we know the integrals of the simpler functions. Okay, so, let us try with these properties. Now, assumption is that f of x and g of x are integrable over a b. So, that means their integral exists. So, now the first one is f of x plus g of x, which is the sum of these two functions, that is also integrable, because f and g are integrable, f x plus g x is also integrable. And that is easy to see, because in the Riemann sum when you take C I, for every C I the limit exists. So, you take any C I for f x plus g x, then you can split that Riemann sum to a Riemann sum for f plus a Riemann sum for g, and in the limit they will become integral f x plus integral g x. Therefore, it is integrable, and their sum, integral of the sum is equal to sum of the integrals. Similar thing goes for when plus sign is replaced by minus sign. And suppose k is any real number, that is a constant, then k times f x, which is another function, that is also integrable, and again similar things hold, that is integral of k times f x equal to k times integral of f x. That also follows directly from the Riemann sum definition. So, we go to the next one. In all these things we assume that a is less than b. So, suppose c is a point in between a and b, then you can break that interval into a to c and c to b. So, what it says, that the integral over this whole of a b will be equal to integral over a c and plus integral over c b, which is easy to see, because this is anyway area. So, area bounded by this. So, if you draw a line here, the whole area is equal to sum of these two areas. That is what this property 3 means. Suppose f of x is less than or equal to g of x at every point x in a b. So, g is dominating f. Then the same inequality also will hold for the integral. That is also clear from the Riemann sum definition. And if you see geometrically, it means something, some f is here and g is lying above it, maybe some point it is equal, something like this. So, then the area under g will be bigger than area under f, that is what it says. Now, suppose f of x is bounded over this a b, where small m is a lower bound for f x, the set of all functional values of f, where x varies from a b, and capital M is an upper bound for that set. So, m less than or equal to f x less than or equal to capital M for every x in a b. Then something similar holds for the integral, but now we multiply b minus a both the sides. So, region is very clear geometrically. You have some function and you have this area, that is the integral a b over f x. Now, if you take m as anything which is smaller than that, smaller than the minimum or smaller than every f x, say this one, this is your m times b minus a, and if you take capital M is anything, any upper bound of f x, so something like this is your capital M. So, this is capital M, then you see that rectangle is m times b minus a. So, the area lies between these two rectangles, that is what it says. Now, next property is not so obvious looking. What it says? It is called the mean value theorem for integrals, just like our mean value theorem for differentials, which we just write mean value theorem. Here we have mean value theorem for integrals. So, assume that f of x is a continuous function on a b. Then it is integrable, of course, it is integrable, we know, but its integral will satisfy something else. Its integral can be expressed as f of c times b minus a for some c. So, which geometrically means if you have some function, so this area is equal to area of some rectangle, where this height is say c. So, that is what roughly it expresses, that this area can be seen as a rectangle of height c, where c lies between a and b. So, in between a and b you can choose some c, where this area will be equal to area of the rectangle, that is what it says. Of course, we will give proofs of some of these, others are obvious, which like 1 and 2 which we have seen earlier. Now, seventh property says, suppose that f of x is continuous on a b and it has the same sign on a b, right? Either f of x is greater than 0 or it is less than 0. If equal to 0, of course, you can do something. Okay, let us say same sign means including equal to 0 also. So, suppose f of x is continuous on a b and it has the same sign on a b, f of x is greater than or equal to 0 throughout. Now, in that case, if f of x integral is equal to 0, then f of x will be identically equal to 0. Okay. So, this is looking a very non-trivial kind of thing, but it is not very well so. Like suppose you have is the same sign, so let us say positive or even equal to 0. Now, if the function is not equal to 0, that is it is not this coinciding with the x axis, then the area can never be 0, area will become positive, that is what it says in this case. Similarly, if you have some negative values and it is function is integrable, and if it is not identically 0, then this area will not be identically 0. We see the contraposition, that will be easier to see. Okay, so, I think these properties are fairly easy and they are intuitively all right, but we have to see some of the proofs how to give them. So, 1 and 2 follow directly, we do not see. 3 is also directly, there is nothing we have discussed already. Okay. Now, along with 3 we have another point. See, 3 says integral a to b equal to integral a to c plus integral c to b, where our assumption is that a is always less than b and c is a point which is in between a and b. So, now we will make it a convention that if c is outside this interval a to b, let us say c is bigger than b somewhere here, then a to c plus c to b will also be equal to this. So, that means along with this we assume that if c is bigger than b, then integral c to b equal to minus of integral b to c. So, this we put as a convention, because that is not covered in the definition. So, we will put this as a convention, so that the upper integral you can see integral a to c minus integral c to b. So, if you transfer it to other side, it becomes a to b plus b to c is equal to a to c integral, which is what we have shown in the property 3. That is why we put this convention, so that we will need not have to worry whether this upper limit c is bigger than a or it is not. The same symbol will carry over the meaning. So, this is an extension of the definition as a way of convention we are putting it. Even if C does not belong to AB, we will assume that this property holds. So, now we come to the fourth property, which is if f of x is less than or equal to g of x for each x in AB, then integral also will satisfy the same inequality. Okay. So, now how to do it? We have f is less than or equal to g implies integral over f is less than or equal to integral over g from A to B everywhere. We will see it from the definition directly, because you take any partition for computing the integrals of A and integrals of g. Suppose you take a partition of the closed interval AB and take any choice set, that is C I should be in between the consecutive points x I minus 1 and x I. Then since f of C I is less than or equal to g of C I, we get f of C I times this, g of C I times this, and their sum, that is also less than or equal to this. That is S f p c, the Riemann sum for f and Riemann sum for g are also related the same way. S f p c is less than or equal to S g p c. Then when you take the limit of that as norm p goes to 0, we get the integral. So, that is quite straightforward. Now, we come to the fifth one, where we have m is less than or equal to f x is less than or equal to m, then that would give m into b minus a less than or equal to integral f x less than or equal to capital M into b minus a. That is our fifth property. So, that is easy to see now, because what we do, we take the g 1 x as constant function m, g 2 x as constant function m, so that we get m, that is g 1 x is less than or equal to f of x is less than or equal to g 2 of x. So, that will give the integral of this g 1 x is less than or equal to integral of f x less than or equal to integral of g 2 of x. And what is integral of g 1 x? By property 2, we see that it is equal to m into b minus a. So, you get the inequality that this integral is less than or equal to capital M into b minus a. That is how the proof will go. So, it is just an application of the fourth property. Let us come to sixth one. So, sixth one is mean value theorem for the integrals, which says that you will have some point C, where the rectangle at C will be equal to that area of the function, right. A to B area should be equal to rectangle for some C. Okay. So, that is what we do. We choose okay, let us write alpha equal to this 1 by b minus a integral a to b f of x. So, this is a real number. Now, due to 5, we see that m less than or equal to alpha less than or equal to m. Why? 5 says between m and m, if the function lies, then integral will lie between m into b minus a times similarly m into b minus a there. So, when you divide by b minus a, your integral divided by b minus a will lie between small m to capital M. That is what we say, that m must be less than or equal to alpha less than or equal to m, where m is minimum of f x and capital M is maximum of f x. They exist because we have assumed that it is a continuous function on the closed interval a b. So, since it is continuous, by intermediate value theorem, we find a C such that f of C equal to alpha, because alpha lies between the minimum and maximum values of the continuous function f x. So, alpha is achieved at some point. So, there exists a point C inside a b such that f of C is equal to alpha. I think that finishes the proof. Okay. Why? Because f of C equal to alpha, which means f of C equal to 1 by b minus a integral a to b f of x dx. So, mean value is achieved there. That is why it is also called mean value theorem for integrals. Let us go to seventh one. So, what is the seventh one? Let us see it again. Seventh one says, if f of x is continuous on AB and it has the same sign on AB, that is a crucial assumption, then integral equal to 0 will imply that the function is equal to 0, right. So, it has the same sign, that is an assumption. Now, it can happen that f of x equal to 0 already, so there is nothing to prove, fine, but that is the conclusion. So, assume that it is not equal to 0, that is, say f of x is greater than or equal to 0 for each x in AB. So, a similar proof will go for f x is less than or equal to 0. But since we say that f of x is not equal to 0 for every x, there exists at least one point t inside the interval AB, where f of t is bigger than 0, right. So, because this is not equal to 0 function, but it is greater than or equal to 0. So, there is at least one point where its value is positive. Now, you use continuity. So, we have the sign preserving theorem for continuous function, which says that there is a neighborhood of this t in which f of x remains positive, right, throughout that neighborhood. So, that means neighborhood is of course some open interval, but again inside that we can choose a smaller delta. So, that there exists a closed interval t minus delta to t plus delta, on which f of x is bigger than 0, right. So, f of x is bigger than 0 for each x in closed interval t minus delta to t plus delta. Then its integral will be greater than 0. We just apply the earlier result, right. So, its integral is bigger than 0, but our integral is always greater than or equal to 0, is equal to 0, that is given. Our assumption that if the integral is equal to 0, then f is 0, that is what we wanted to show. So, we have started with, suppose it is not equal to 0, but it is say greater than 0, greater than or equal to 0, that is first case we are taking. Then at some point it is bigger than 0, so that we get integral over that smaller neighborhood where it is always bigger than 0. Since f of x is bigger than 0 always, so its integral is also greater than 0. So, that contradicts the assumption that integral is equal to 0, because nowhere it can be negative, f x is greater than or equal to 0, that is given. Okay. So, that is the contradiction. To see the other way also, you can formally define some g x, which is f x if x belongs to a minus delta to a plus delta, and 0 if x does not belong to a minus delta to a plus delta. So, that means you have some point a here, you have a minus, it is not really a, it should be t minus delta to t plus delta. Okay. So, in that t minus delta to t plus delta, you take as f does, and then everywhere else it is 0. Okay. That is how the function looks like. So, the area under this will be really this area only, and that is always less than or equal to f x, and that is already bigger than 0. So, f x integral is bigger than 0. So, it is telling in detail from this greater than 0 integral over t minus delta to t plus delta greater than 0, how to use that to conclude that integral over the whole of a b is greater than 0, that is all here. So, that proves the result. Now, if f of x is less than or equal to 0, you can everywhere use less than instead of greater than, and the same argument also proceeds, right. It will give the conclusion that integral f x is greater than 0, which is wrong. Okay. So, these are fairly straightforward results to remember. It is just coming from our intuition that it is the comparing the geometrical areas with something else as the case demands. Okay. So, we will be really going to application of these results, but before that just for 1 second, why we have explained why it is called mean value theorem for integrals, because this number which is integral of a to b f of x dx divided by b minus a is also called as the mean value of the function f, because anyway it is the sum of this, it is the area divided by the length b minus a, that is why it is called the mean value. So, property 6 says that mean value theorem for integrals, that the mean value is achieved right, by the function in some sense. So, it is f of c is equal to this. Okay. So, there is another thing to note which will be useful many times. If you have a to b f of x dx and you have the integral a to b f of t dt, they are really same. It does not matter what this variable is, right, because anyway you will be taking the Riemann sum. In the Riemann sum you do not have any x or any t, it is the area below f x or f t is the same thing, because the curve is same. So, that is what we say the definite integral does not depend on the independent variable. Okay. So, with this let us go to the convention what we are talking earlier, that in the notation a to b f of x dx we always assume that a is less than b. But if a is bigger than b or a is equal to b, we can give some meaning to the integral which will be consistent with our properties, right. If it contradicts some of the properties, we should not put that convention, otherwise we can use the convention. It is a really redefinition of that idea for the case where a is equal to b or a is greater than b. If a is equal to b, we will put its integral to be equal to 0 for any function f x, and intuitively what it says, that you have a function which is defined at one point only. So, the area bounded by that curve and the x axis and the line x equal to a and the line x equal to a is 0, that is what it says, and that is clear from the geometry also. So, we put this convention, if a is equal to b, then integral is equal to 0 whatever be the function. If a is bigger than b, so we will put a to b f x dx equal to minus of b to a f of x dx. This will go along with our property 3 and 4. So, again if a real number c does not belong to a b, then both these integrals a to c f x and integral b to c also exist. In that case, we will say that a to b f of x dx equal to a to c f x plus c to b f of x. As we have seen, if c is say bigger than b, then a to c and c to b will become now b to c with negative sign. So, this complies with our earlier property, right. Similarly, if c is less than a, then a to c will be minus c to a and this is c to b. So, their minus will give us a to b again. So, we put this as a convention because it is consistent with our property. So, now when an integral appears in the form a to b f of x dx, we need not assume that a is less than b. Of course, that is the case, crucial case which will decide everything, all its properties. Even if a is greater than b, it is alright, it will be negative of integral b to a f of x dx. That much is enough for us to remember.